and just view this so you guys can see this for later. Okay. 16 and 18. While training for a biathlon race, Kevin covered a total distance of 9 kilometers by swimming for 45 meters and running for 20 meters. The next day, he swam 30 minutes and ran for 40 minutes, covering 14 kilometers. Find his rates for swimming and running. Okay, so how many variables are unknown right away? How many unknowns are there is my first question. Finding the swimming rate, the running rate, we have total time, we have time it took for each individual piece. What are the unknowns? How many are there?
The swimming rate and the running rate.
All right, so let's start with that. So R and S, you want to use? Does that work?
Yeah.
So let R equal the running rate, and let S equal the swim rate. Please, guys, use these whatever these are called, quotes. Use quotes. Don't write the whole thing out twice, especially if it's like a long slew of words. In the first example, we're told that Kevin covers a total distance of 9 kilometers, and we're given something about his time, and we know that rate times time equals distance, right? So my governing formula I need to remember is this. D equals RT. In the first formula, I know that Kevin covers a total distance of 9 meters. So I could say D1 plus D2 is 9 meters. Or just 9 for now. But D1 is the distance traveled when he runs. And it says that Kevin runs for 20 minutes in the first one. So that's going to be the rate he runs at times 20 minutes. So I'm replacing D with R times T. That's when he's running. He's also swimming, it says, for 45 minutes. So let's use the swim rate S. And that's times 45 minutes that he's swimming for. And that's going to be 9 kilometers total. So again, running for 20 minutes, swimming rate for 45 minutes, a total of 9 kilometers, because this is really distance, this is really distance, distance plus distance equals distance. So this is a distance equation. Does that make sense? I kept talking about labeling the equations of dollars and stuff. This is a distance equation. Turns out that the second scenario given is also a distance equation. That's just your second part. You're told in the other piece that the next day he swims for 30 minutes. Bless you. So let's put S times 30. He swims for 30 minutes and he runs for 40 minutes. And although he runs and swims at different times, he does not cover the same. He covers a different distance, 14 kilometers here. But these are the new rates on the second day. And that's okay. Let's go to 18 next. I'm not going to solve this by hand. How am I going to solve this? Okay. 20, 45, 9, 40, 30, 14, RREF, enter, you're done with the problem. I mean, it's more than that, obviously, to get into it and stuff. And if you're really struggling and you're forgetting, literally type in YouTube, solving a system using RREF on a calculator, guaranteed 50 videos off the top of my head. Like literally, there will be 50 good videos you can see. So if you're really struggling and you just missed what I did, I'm not going to go over this all again on the calculator.
So in the question it asks for rates in kilometers per hour.
Alright, so
I changed that to like fractions. Is that okay?
That's what you should do. I didn't even look. Is that what it definitely says? Yeah, find his rates in kilometers per hour. So this would give me the answer in kilometers per minute, and then I could alter that at the end. Or you could alter it earlier. So that's fine, Maura. So Maura said he made this 1/3, 2/3, 1/2, and 3/4. Does that make sense? He put all these minutes into hours. You could find the rate in kilometers per minute, and then convert that to kilometers per hour afterward. It's the same difference. But Maura, I think your method is probably better. Okay? Because it's already in hours by doing it that way. So your matrix for this would be the following. Oops. In hours, right? Okay, that would be my matrix to solve. If I converted these into hours first, divide by 60 everywhere, please. Divide by 60 and reduce where possible. The other question was 18. 18 is another good one. I'll leave this up for a minute, actually, until we're ready. It says for 18 that a certain mill, a mill where it produces stuff, it costs C in thousands of dollars to produce X tons of steel. And we're given a cost equation. We're then given the revenue equation after that. Hey, how are you? Good. Can I call you back in like 2 minutes? All right, thank you. So in the cost and revenue equation here, the question, we're given a cost function and a revenue function. The question says to graph each equation on the same coordinate and find when the revenue equals the cost. They call that the break-even point. Revenue, money, you bring in. Cost, money, you send out. If you bring in the same you send out, do you make any profit? You're even, right? Break-even point. When do you make profit? When the money you bring in is more than the money you send out. So in this problem, it says that hypothesize that this is what it would look like. Actually, I know what it will look like. Sorry. Cost starts at 3.5 with a slope of 0.3. I'm sketching this literally from scratch. I'm not using numbers right now. Revenue has no y-intercept but has a slope of 0.5. So what does this tell me? This is basic economics here. In the beginning, when you start mass producing something, are you going to make profit in the very beginning? No. What do you have to pay for? You have to pay for the machines. You have to pay for the warehouse space. You have to pay for your employees. So in the beginning, when you're not producing much, you're not going to make much. That's not much production in the beginning. Isn't your cost above your revenue? And then eventually, your revenue starts to go up as you produce more and more of these items. Called this X. X is the tons of steel produced. As you make more steel, the Bessemer process became mass production of steel, which is what made it so much cheaper to use. It was just an optimization process. That's all it was, the Bessemer process. So the cost eventually becomes less than the revenue, and eventually you have more revenue. So this problem said in part B to find where they intersect. That's right here. This is called the break-even point. So if you stop production at that point, you'd have no profit at all. You've just kind of wasted your time. You wouldn't lose money, but you wouldn't gain any money, right? You want to gain money, and I can see that there's a differential. Pick any 2 points now, here and here. Look at the gap. That's your profit margin. That's why it's called margin, by the way. Anybody ever knew that? Have you heard the phrase profit margin before? Margin? The margin on the paper, isn't that the space, the gap? That's your profit margin right there. Physically, geometrically. If you literally calculate the height of line R and subtract the height of line C, you're left with a line segment in blue. That's the profit margin itself. So that's what this problem is asking about for part C. It says, what does the difference of R minus C for when X is greater than this represent? It pretty much represents profit margin, which is in blue. Okay? I wouldn't focus as much on this for this test. I gave you this problem. This is really going to be used more in sections 3.8 and 3.9 when we get to functions and we start to look at slopes and what they mean for graphs. Kind of like what we did with the line of best fit activity with the graph, and you look at the slope to see what the slope at. Same concept here. Okay, good question, Isabel. Yes?
I have one question. I died, so I don't
Yeah.
remember it, but I think it was question 5 from 3-4.
35 and 3-4 gives you a point and another line. Is that the kind of question you're talking about? So the point given is 2, 0. And we're told that the line given is x plus 2y equals 3. And we want to find a line that's parallel and perpendicular to this other line that goes through the point given. Is this what you're thinking?
Oh, okay. I see. You just make this so.
Well, let's quickly do it. But if I wanted to do this, I know that I'm given this point already. I can look at this one, and I can say the slope is negative a over b, which is negative 1 over 2. Agreed? So there's my slope. So if I want a line for part A, it says parallel. So I'm going to use the slope equals negative 1/2, and I'm going to use the point of 2, 0. And I would leave it in point slope. I would just leave my answer like this. Okay? I can obviously drop the 0 because it doesn't matter, and it'll end up looking like slope intercept. But there's no need to distribute the negative 1/2. If it doesn't say to put it in slope intercept or standard form, leave it in point slope form like this. Part B, though, wants it to be perpendicular to the same point, though. Same point still, 2, 0. but the line should be perpendicular, so we'll use the negative reciprocal, which is 2 over 1. Okay? And that's it for this problem. You could have gone further, and if you really did, this becomes 2x minus 4, this becomes 1 half x minus 1. And that's just y, and that's just y. By all means, you can simplify. But if it's not asked of you to put it in a certain form, leave it in whatever form you get it in first. Is that reasonable to say? So you're not wasting your time manipulating forms when it's not asked of you. If it's a multiple choice, obviously your answer, whatever form is given, it needs to be changed to, right? For multiple choice. If I give an answer in standard form, how would I get this back to standard form? What would I do to put this to standard form? I'd probably
Just simplify that, distribute it, and then get x onto the other side.
Yeah. Distribute the 2 and then move the x over. Okay, if I wanted this in standard, for those that have been struggling with putting things in standard form, this becomes this. That's slope-intercept form, right? If I distribute the 2, there's so this is point slope. This is slope-intercept. And then standard would be moving the 2x over. But I would actually move the y over and switch the y in the 4. Leave 2x as a positive. It doesn't really matter. Okay, I would add the 4 over as a positive 4, subtract the y, so it becomes 2x minus y equals positive 4. I'm just going to write in that direction. But those are my 3 interpretations of that answer. Okay, they're all the same exact thing really, though. They're not changing at all. Okay. I need a phone call for like 3 seconds real quick. That was Miss Gill filling about something that's important for the next 5 minutes. So we looked at 3-4, the idea of it. We looked at parallel and perpendicular lines. We looked at systems. Come up with a 3-7 question we want to go over. Somebody pick out one that was important real quick.
Oh, you have 3 6. Wait, how many can you put on?
Three seven. Let's go. What are we thinking? Let's do a good example that will help us for tomorrow's test. One of the problem set examples was good, maybe. I'm leaving it up to you guys to pick one more. Go ahead. 35. Number 35. 3-7. Number 35. Number 35. Here it is. Okay. More. I like it. Good job. All right, because we have conditions also. That's what I wanted to see. So 35, and you know what I'm going to do? Did you guys, first of all, did you feel confident on 35, those who did it with the problem set? So I'm going to make it a little harder, okay? I'm going to tweak 35 a little, but I'm going to use the basis of it. Instead of x being greater than or equal to 0, I'm going to start with x is greater than or equal to 1, just to make it a little bit trickier. And for the y part, I'm going to use y is just greater than, instead of greater than or equal to, and I'll put y is greater than negative 2. Let's change those, but I'll keep the other two the same. So let's leave x plus y less than or equal to 6, and x minus y less than or equal to 2. Hopefully this will work. Still, if it doesn't, we'll discuss why it doesn't and it does work. So when you approach a problem like this, there are 2 ways to start it. I can graph the lines that are diagonals first, the ones that have slope, and then apply those conditions of x and y, which are given first. Or I can start my problem by applying the conditions for x and y and then graph the lines only in those regions. It does not matter which way I do this. Now, because x is going to be greater than 1 and y is going to be greater than negative 2, I don't really have to do much more than use my first quadrant and some of my fourth quadrant. Does everybody see what I'm saying right now? For x greater than or equal to 1, that means that I can only focus on the graph after x equals 1. I'm not concerned with it elsewhere. So I'm not worried about everything to the left of that. And y equals negative 2 is down there. So I could start by putting a solid line right here, going through x equals 1, a dashed line through y equals negative 2, okay, take a look. Again, and I should label my x and y axis, sorry, so we're clear on what those are. I haven't labeled my y axis yet on the increments for a reason, for an obvious reason, for some, I guess. What I notice here, though, again, this is x equals 1, this is 2, this is 3, this is 4, this is 5, negative 1 for y, negative 2 for y. I notice that these are both greater than statements. So this means I shade to the right of x, vertical line. This means I shade above the horizontal line. So my domain and range of interest in this problem really is this region right here. Look up where I'm pointing. I'm not shading for a reason. It's this region right here. That's my only interest at all. So please mentally point that out to yourself or physically give it some sort of a shading to start. So I know that my answers can only be in this region to start. I already have that piece stated with those inequalities. But I have to graph the linear function still. X plus y less than or equal to 6. What's the easiest way to graph this? And please think before you answer.
I just put it into slope and use that form.
It's not the easiest way though. I get it, because it would be y equals negative x plus 6. You go up to your y-intercept of 6, do your slope. I get it for sure, Isabella. But there's a faster way to graph this when it's in standard form. Find the x and y intercepts. They're both 6. Look. That's how you find them. Just cover it up. 6, 6, 6, 6. They're both 6, right? Just makes life so much easier for me. So take the shorter route, please. So let's go up to 6 on the y-axis. Whoops. Let's put a dot. On the x-axis, 1, 2, 3, 4, 5. I got to go a little further. 6 is out here. And connect those two dots. Connect those two dots. Since it's less than or equal to, it's going to be a solid line. Here's my other part of the function. I know, we'll get into that in a minute. So it's a solid line. The last one here, the x and y intercepts. The x-intercept is just, read it. And the y-intercept though? Careful. Negative. Get y by itself, divide by negative 1, right? The y-intercept is negative 2. It's down here. The x-intercept is positive 2. It's right here. We'll graph that one. All right, so let's take a look at what we've got here. We're told that x has to be greater than 1. Okay, it is. We need these functions to be below those numbers. What do I want to test? What point is a good point to test? What point should I test, Maura?
0, 0.
Yeah, the origin. So let's focus, and you need to look up to see what I'm pointing to. Let's focus on this line first, please, okay? Everybody focus on this line. We go to the inequality that gave this line, and it is right here. 0, 0. 0 plus 0 is 0. Is that less than or equal to 6? Yes, right? So I shade everything on the side of 0, 0 for this line. So here's this line. Let me use another color. Colors are very nice here, by the way, to use on your iPad. It makes it easy. I'm going to shade everything on that side of the line. And notice that I did go a little beyond the line and beyond the gray areas, but only where the gray area overlaps is my solution so far. So right now, where the red and the gray overlap is my solution region. What kind of a shape do I have right now? Come on, geometry. I know two of you took geometry. If I were to look at this region right here, it would eventually need, what kind of a shape would I have? It'd be a triangle, be a triangular region. Again, because eventually this line right here follow my fingers, or my pointer here. This line right here will meet up with this line over here. Are both showing at the same time? They're not. Why does that not work? Here we go. These lines themselves, the ones I'm pointing to right here, will eventually meet at some point down the road. Okay? And you'll get a triangle there. My last, though, I have to apply is this. I plug in the origin. What line is this referring to, though? It's referring to this line now, right here. Okay, the one that we're tracing. When I test the origin, here's the origin right here. If I test the origin, the statement is true again. So I have to shade that side. I need to use green now as a different color. So I'm going to start shading with green on this side of this line. So let's take a look. Where is my solution region in this problem? Physically, where is it? What do you think?
It's the triangle that's like with when all three are shaded.
Yeah, it's the triangle right in the middle where all three are shaded. Which inequality did not play a role? Which inequality didn't actually play a role?
Y is greater than -2.
Yeah, this one doesn't matter as much because it looked like these lines intersected here anyway, so the answer wouldn't have gone below this vertex, it turns out. This vertex would have been my minimum here. You couldn't have gone below this because of that intersection. So it turned out that this didn't play a role. Okay, it doesn't actually affect your answer. So if I'm labeling my solution region, it's right here in the middle. Whoops. Dang it. It's right here in the middle. Okay, and I'll put it with a little bit more intensive highlighting. It's that triangle that I'm kind of shading. I'm bolding the triangle. Can you see it? Okay, I'm bolding that region in the middle. That's my solution region right there. Why did the y equals y greater than -2 play a role? Because I can see that it didn't affect the answer. It didn't mean anything. If I didn't have that there and didn't shade that, it still would have been the same exact answer. Nothing would have changed. And that's so you can see what constraints are not actually binding. It's a non-binding constraint is the word. All right, other questions you have still? 1, 3, 4, 3, 5, 3, 6, 3, 7. We still have a couple minutes. Yeah, go for it.
3, 4, number 43.
3, 4, number 43. Okay. Number 43 says the following. Find an equation. Let me open a new slide. Find an equation in standard form. So here's what I think right away. That, in number 43 says, having a y-intercept of 6 and parallel to the x-axis. This one? So when I visualize this, a y-intercept of 6 is right here. Parallel to the x-axis means the line looks like this. So it's parallel to the x-axis, right? And any horizontal line is always y equals some number. What number is that? In this case, it's just whatever the y-intercept is, 6. Okay? So you don't have to worry about it because if it's parallel to the x-axis, the slope is 0. So you could have just done this. Right? Which becomes... And how do I put that in standard form? It's really just... But do I write that? No. So this really is just my answer. Okay? You don't have to worry about the 0x in standard form. It's just 0x plus y equals 6. Okay? Others. You're going to see that you're going to use this next year in geometry a lot with geometric coordinate proofs. You might be given like vertices of certain shapes and being told to prove that the sides are parallel for parallelograms or trapezoids, or prove that certain sides are the same length, or proving triangles congruent or similar, depending on what the question is. But this concept will be used again of graphing several lines at once. I did want to go over intersection method on the calculator. Take out your calculator real quick. I'm going to verbally give instructions here because we're going to run out of time for that. It's very easy actually, so I think you won't have a problem. Don't play games on a calculator. Let's make these our graphs, please. please. Now, instead of negative 1/3, make that negative 2/3. Make that negative 2/3, please, not negative 1/3. Okay. First thing you have to write. You need to have it in slope-intercept form for it to be able to be put into the calculator. So if you're given it in standard form, you're given it in point-slope form, put it in slope-intercept form for the calculator. Put one of them in y1, put the other one in y2. If I'm putting this in y1 and y2, first of all, make sure your negative 2/3 is written correctly. So I would be putting in y1, my thing would literally say this. That's pretty obvious. But in y2 right now, I would have the following. That's what it should be. The X button is right below mode. If you haven't jumped to find the X command, look below the button mode, that's your X button. Now, once you have these two in your Y1 and Y2, press Zoom 6 for now. Press Zoom, which is in the very top middle of your calculator, and then it's 6, just to come up with a standard graph for now. Zoom 6 standardizes your graph. It allows you to graph from negative 10 to positive 10 on the X and Y axis. Now, I know one of your graphs is going to have a y-intercept of 7, so it's going to look like this. That's what one of your graphs should look like right now. The other one has a y-intercept of 13, which is probably off the graph. Okay, it's probably off the graph. So what you need to do is recognize that you're not going to see a lot of it. Do you actually see any intersection at all right now? Good. You don't, right? You don't see an intersection at all. That's what I wanted. Thank you. So it's probably like this. You're probably just seeing a line come in from the top. Is that what you're seeing right now? So do this. Ready? This is what I did this on purpose. You don't want to always assume that this is going to give you the intersection. Because when it comes to cost and revenue, the cost intersection might be like $20,000. So you need to change your y-axis because you're not seeing enough, right? So everybody press window. It's next to zoom. Press window. And go to your y-max and make it 20. Because we know that the y-max we care about is going to be 13. That's our y-intercept. So I'm choosing 20 so I know I'm above the highest y-intercept. I want to be above the highest y-intercept. So choose 20 for the y-max, and then press graph. Don't press zoom 6 again. So choose 20 for the y-max, and then go to the far top right button and press graph. Once you can everybody see the intersection there? Press. I'll get to you one sec. Press second, and then press trace. That brings up the calculate feature. Press second trace to bring up the calculate feature. Remember we had these blocks on earlier? That was on, so just turn it off. Now you want to change your window, go to your y-max, make it 20, and then hit graph. So, second calculate, what are you going to choose, obviously? Intersect.
How do you choose where's trace?
So second and then trace, it's up on the top. It's next to graph. Yes, it's next to graph. Second trace, and then go down to intersect, hit enter. It's going to say the following. Try to stay with me, please. Second trace, intersect. It's going to say first curve, question mark. Just trace over to the intersection. Use the arrow keys, left and right, and the arrow keys. Try to go toward the intersection. It doesn't even matter if you do this. You can just press enter, 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 and it'll find the intersection. It's only important when you have multiple intersections and you have to specify which one you're looking for. You're never going to have that with linear functions because a linear function only intersects once or none. But later on in this year, we're going to do this. Take a look, please. We're going to look at functions that intersect multiple times. A quadratic with a linear. Then it matters that you trace over to the nearest intersection that you're looking for. But on our graphs, if you have an intersection, as soon as you press second intersect, or second trace intersect, just press enter, enter, enter. First curve, enter, second curve, enter. It'll say intersect, just hit enter again. And it'll give you the intersection for sure.
So I sent the graph now.
Second, trace, intersect. Enter, enter, enter. One more time. There it is. Calculating intersection. Here's your intersection. This is literally what a matrix is doing, but this only works for systems with two variables. Because if I have x, y, and z, how can I graph that? Only x and y can be graphed, right? Only when you have two variables. So for a system of equations with two variables, you can solve by graphing instead of using the matrix too. It works just as well. But with three variables, you cannot solve with this method. Okay, I have graphing. Is that clear what I'm saying? You don't have to worry about finding the intersection because you're not doing this. Later in the year, we will focus on that more. All right, please be well prepared for tomorrow. Multiple choice, as always. A couple short answers, as always. And then where do you think the word problems are coming from? Yeah, it's going to be the 3-6 section, right? Maybe review some of your old problems, your class problems, your problem set type problems, any other 3-6 problems you want to explore.